Okay, so in this video, guys, we're moving on from the previous topic in the thermodynamics section of the A21 chemistry, where we looked at previously Born-Haber cycles and lattice enthalpy calculations based on that. We looked at the reasons for the different values of lattice enthalpy from the experimental value, so for the Born-Haber version versus the theoretical value. Now, you don't have to be able to calculate the theoretical value, but you need to be able to explain why there may be a difference between it and the experimental value. We also looked in the Born-Haber and lattice enthalpy topics for the reasons as to why lattice enthalpy may be larger or smaller depending on the charge and the size of the ions within that particular compound. Okay, so you should be able to do all of that as well as draw the cycles and do the calculations based on them. Today we're going to move into the next topic in the thermodynamics section of the A21 chemistry, and that's to do with the energy changes essentially whenever we dissolve or try to dissolve an ionic compound in water. So there's three energy changes that we need to be aware of here. Two of them are on the board at the minute, the enthalpy of solution and the enthalpy of hydration. And the third one is one that we've already covered, which is the enthalpy of lattice energy dissociation, which we looked at in the previous topic. So let's get started. I'm going to work through the theory of this, and then at the end of this PowerPoint there are some past paper questions. I'll work through a couple of worked examples during the PowerPoint, and then what I would suggest that you do is have a look at the past paper question, pause the video, do it, and then the answer will pop up a few seconds shortly after the question. Okay, so let's have a look at, first of all, what sort of energy changes are actually involved and what goes on at a molecular level when substances actually do dissolve. So you get hydration of an ion. So if we look at this equation here, this is just a simple little equation to show what happens when you dissolve a solid ionic compound. Sodium chloride is the one we've chose. I could apply it anyway. And what you essentially end up with are the free ions dissolved in water, surrounded by water molecules. We'll have a little look at that in a bit more detail in a slide or two. Well, what I want you to appreciate here is that if you think about it, every electrostatic attraction between every sodium and every chloride has had to be broken here. So we've essentially had to break all the ionic bond within, in this case, 1 mole of the sodium chloride to get this to dissolve. And you might, perhaps those of you who are on the ball might start thinking, well, that's probably going to involve the lattice energy of dissociation, and that will be exactly true. Okay, so when those ions are free, they combine with the water and they form bonds with the water. Okay, until eventually we get a homogeneous mixture of that compound, which is surrounded by water molecules, the individual ions surrounded by water molecules in solution. Okay, so obviously the ions, when they break free of the solid lattice, they start to form attractions with the water molecules, and those attractions are ion to dipole attractions. And hopefully you can see what I mean by ion dipole attractions. The ion, obviously the sodium is an ion, and the chloride is of course also an ion. Water is a polar molecule with a delta positive end and a delta negative end. And if you were asked to draw a diagram, this would be the sort of diagram you would draw to illustrate the relationship between the metal ion and the non-metal ion and water. So essentially the water, the delta negative section of the water, as you would expect, is attracted towards the positive ion and vice versa. Actually, sodium, we've just simplified this diagram by just showing one water molecule, but actually sodium has the ability to become surrounded by 4 water molecules. I don't think in any diagram you would necessarily need to show all 4 in examiners, just looking that you understand that the positive or negative ions are indeed surrounded by water molecules. The actual number in this case maybe not so important. Okay, So you get the idea. What you might also pick up from this is that there's energy given out here, because we are, if you look at it, we are now forming a bond and attraction between the water and the non-metal, and the water and the metal ion, okay? And both of those interactions, okay, will give out energy. Now, you will hopefully also have recognized earlier that when we have the solid and we break that solid up and solvate it, okay, when it becomes dissolved in water, it takes a certain amount of energy to overcome the electrostatic attractions which are within that. So that requires energy to be taken in. It's an endothermic process. So you have energy being given out and you have energy being taken in here. Okay, and these two factors will be important in terms of determining whether or not this solid actually does dissolve. And we'll have a look, there's another energy change as well on top of this that we have to take into consideration. So the number of water molecules, as I said, there's sodium, has the ability to be surrounded by 4 water molecules. The number of water molecules that surround those negative or positive ions is called the hydration number of the ion. Okay, I think that's fairly obvious what it's called, the hydration number, the number of water molecules. Sodium has 4, magnesium 10, and aluminium are rather significantly larger, 24. Now you might be asked to consider, well, why would that be? So maybe pause the video and have a wee think about it and then come back to the answer. So if you pause it now. So the answer to that is that sodium is the largest ion of the 3 of those, and it only has a +1 charge. Okay, so in other words, it has a +1 charge spread across a fairly large volume of space. Magnesium is more charge dense. It has a 2+ charge over a smaller volume of space, and aluminium is the most charge dense of the lot of them, and is a 3+ spread over a very small volume. Okay, so therefore, basically, the aluminium is able to attract much more strongly because of its increased charge density, many more water molecules, and hold them in a hydrated shell of water molecules around the positive metal ion. So, in other words, it's to do with ion charge and ionic radius. Very similar to lattice enthalpy, in fact. Okay, so from the previous slide, okay, you can see that bond formation occurs. A bond formation we're talking about is between the ions and the water that I spoke about, and that of course gives out energy and is an exothermic process, and that energy is needed, as I said on the last slide as well, to overcome those electrostatic attractions between the ions. Okay, so you're always looking for, in any solubility exercise here, you're looking for the amount of energy that is given out, really to exceed the amount of energy that's taken in to break up that lattice. So a couple of definitions. You have 3 definitions that you need to know for this topic. Lattice enthalpy, which you should already know. The enthalpy of solution, which we'll look at on the next page over. Okay, and the enthalpy of hydration, which we'll look at now. So the hydration and solution enthalpies are similar, so try and make sure you learn them well and don't get them confused. So the energy released when 1 mole of gaseous ion dissolves in water in an infinite dilution, and an infinite dilution just means there's more water than you need, basically, and that's measured at standard temperature and pressure. Okay, 298 kelvins, 1 atmosphere of pressure, or 100 kPa. Okay, values that you need to, of course, know. So just draw your attention to the main things, or the main parts of this, guys. We're talking here about gaseous ions. Okay, so you may now start to see perhaps the link between this and lattice enthalpy, where lattice enthalpy was when you broke 1 mole of the solid ionic compound up into its gaseous ions. This is now where we take those gaseous ions and we dissolve them in water. So if we go from the solid to the gaseous ions, that's lattice enthalpy, the gaseous ions to hydration enthalpy, then we now have that solid dissolved in water. We'll create some little Hess's law cycles later to illustrate that. So if you were asked to write an equation to illustrate this, that's the sort of thing that you're after there. Okay, so it's just the gaseous ion, not the gaseous atom, not the gaseous molecules, not the compound itself. So it's pretty straightforward. Okay, and again it'll become more exothermic the greater the charge in the ion, and the more exothermic the smaller the radius of the ion. Okay, so similar to the reasoning that we've had previously. So that's hydration enthalpy. Now let's look at enthalpy of solution, which is a similar definition, but you do need to be cautious here. That's the energy change when 1 mole of a substance. Okay, so when we make reference to a substance, we're basically talking about, for example, just the compound, maybe sodium chloride, magnesium oxide, just the solid ionic compound, not as ions, not as gaseous ions. Okay, so how much energy is given out when that dissolves in water, okay, and at standard temperature and pressure. So if you're asked to write an equation for that, that's the sort of thing you would do on the board, making sure you get your numbers of ions correct, your charges on your ions, and state symbols. Like when we went through the Born-Haber cycle, and I preached on about state symbols, how important they were. Okay, state symbols are key because they're part of the definition. So if you're asked to write an equation based on the definition, they're absolutely key. And the last energy change that's involved in deciding whether something is soluble or insoluble is that, well, from this perspective, there's actually another energy change called the Gibbs free energy, but we'll do that at a later date, is the lattice enthalpy of dissociation, which we looked at in the previous topic. Okay, so we should know the definition for that: 1 mole of an ionic compound converted into its gaseous constituent ions at standard temperature and pressure. And if you're asked to write an equation for that, there's a couple of examples on the board, so hopefully you can get the picture. Again, get your numbers of ions correct, get your charges on your ions correct. Okay, so you can see that the sodium chloride has a much lower lattice enthalpy than the strontium oxide, and again, hopefully you are able to work that out. The sodium is only +1, the strontium is +2, so it's a higher charge. The oxide is smaller than the chloride, and the oxide has 2 negatives. You end up getting a stronger electrostatic attraction between the 2 ions in the strontium oxide than you would in the sodium chloride, and that leads to about 4 times the value of the lattice dissociation energy. Okay, so those are our 3 definitions. Those are the energy changes or the enthalpy changes which control whether or something does or does not dissolve. We need to now be able to put all of those together in a Hess's law type cycle, and then do some calculations to work out the unknown that the examiner has requested, whether that be a hydration enthalpy, an enthalpy of solution, or perhaps a lattice enthalpy. So, like I did when I was doing my Born-Haber cycles, I always started with the 1 mole of the ionic compound. Okay, I think that's a sensible starter point. And we want to dissolve that, so we go from that to the aqueous ions. And for those of you who are on the ball, okay, you would have realized that the enthalpy of solution is the energy change there. Now, then, in order to get to that enthalpy of solution, to get to those aqueous ions, I'm going to have to break every single bond within that compound, okay, because I've got equated free ions dissolved in water in the bottom line here. Okay, so I need, in order to do that, to break every single bond, every single electrostatic attraction, and that would be equivalent to the lattice dissociation energy. And as soon as those gaseous ions are then formed, they will combine, okay, and form bonds and give out energy called the hydration enthalpies for those particular ions. So that is your Born-Haber cycle. That's your connection between those different energy changes. And if we sort of apply Born-Haber, so we're starting here and we're going to here, but we're going via that route. So in other words, if I call this over here delta H1, I call that delta H2, and I call this delta H3. Remember, that will be what you'll have a hydration enthalpy for the positive ion and 1 for the negative ion. Well, then you have delta H1 is equal to delta H2 plus delta H3. Simple as that. Okay, and that's really important that you remember that. So if we were doing it by Hess's law, this is exactly what I've just said. The enthalpy of solution is equal to the lattice dissociation energy plus the hydration enthalpies of the ions. So let's look at an example for potassium bromide. So let's first of all look at drawing our our Hess's law or Born-Haber-Isch cycle. So we take our solid and we turn it into the dissolved ions. There you go, that's our enthalpy of solution. But in order to do that, we've got to break all the electrostatic attractions between the potassium and the bromide, and that is equivalent to getting the gaseous, the free ions, and that's the lattice enthalpy. And then as soon as those gaseous ions are made, they can dissolve in the water. So I will get the enthalpy of hydration of the potassium ion and of the bromide ion together, okay, which are 300, minus 305 and minus 351 respectively. And then I do my calculation. Okay, so if I just remember that the enthalpy change is independent of the route taken, I'm trying to get this enthalpy change here. So that enthalpy change is the delta H1 is equal to the delta H2 plus the sum of the delta H3s. Very simple calculation. Gives us a value of positive 23. So that's an endothermic process, and you might predict from that it's impossible to dissolve potassium bromide because it's endothermic, but in actual fact you can. Potassium bromide does dissolve, and the reason for that is because it's explained by a thing called the Gibbs free energy and the total entropy change, which are topics that we'll do later. So don't worry about the minute if you're coming across substances which have a positive enthalpy of solution value but still have the ability to dissolve. That's not a big problem at the minute. So let's construct another one for calcium chloride. So the only thing that might catch you out here for the calcium chloride is the fact that you have two Cl's to account for. So again, convert everything into aquated ions, calcium ions and chloride ions. That's your enthalpy of solution. Then you remember you have to break all the bonds within the compound, and that's equivalent to the enthalpy of the lattice energy dissociation. And then you have to carry out your hydration enthalpy, so those gaseous ions will combine with the water. And just a wee reminder with the red number 2 there on the left hand side, okay, that you have got two chlorides, so whatever that lattice enthalpy for the hydration of chloride ions at minus 382, you got to multiply that by a factor of 2. Okay, so you can see we've accounted for that down there. So our final answer will be minus 66, suggesting that calcium chloride, and it is, pretty soluble in water. So how do we relate this enthalpy of solution to solubility in water? Well, you would expect if you have a negative or an exothermic enthalpy of solution, you could comment that this solid would be soluble in water, but some positive enthalpy of solution are of course also soluble. So the one we looked at there was potassium bromide. So provided it's not too positive, the enthalpy of solution, you're still likely to get this thing to dissolve. But we will look later on at the enthalpy, the delta G, the Gibbs free energy, and the total change in entropy as well, which are two things that come in a further thermodynamics topic within A-level chemistry. Right, we're going to look at a few questions here. So I'm going to do these ones, and then there's a few coming up which are old past paper questions, so I'll bring up the blank question, and then I'll bring up the solution on the next page. Okay, and you suggest that you just pause the video when the blank question comes up, and then hit play, do the question, and then hit play and check your answer. It should be fairly self-explanatory. Right, so the first thing was explain the term enthalpy of hydration. Well, that's just a definition from your CA guidance. And then use the following data and an appropriate energy cycle. So you've got to construct an energy cycle as part of this question to find the hydration enthalpy of a potassium ion. So we start off with our solid, okay, and that goes to our aqueous ions, Okay, so the same as we did earlier. And we've also got to tear apart every bond within our solid to give us our gaseous ions. And then we get our hydration enthalpy from there. So we fill in our values. We've got all the values bar 1. Okay, so the only value that we are missing, okay, is the one from here for the chloride ion, which is what they have asked us to sorry for the, that's wrong actually, that should be a chloride ion. So the only one that we're missing is the potassium ion, hydration enthalpy. So we'll do our Hess's law cycle again, where we're going to do our, if you like, 1, 2, we'll call that 3A, and we'll call that 3B energy. So 1 equals 2 plus 3A plus 3B. So we're missing 3B here, energy change. Okay. So simple bit of swapping things around, and our answer for that is 305 kilojoules for the potassium. Okay, hopefully you're all able to do that. It's pretty straightforward maths. So here are your questions. So again, I think there's about 6 of these. So if I put them up and then I will pause them, or maybe, sorry, you pause them and then work through them and then check the answer. So I'm going to turn to the next slide in 3, 2, 1. So there's your answer. Okay. So this was just going back to the sort of maybe the first slide earlier, where the negative ion is orientated towards the positive part of the water. Okay, and over here the positive ion orientated towards the negative parts of the water. I just drew 1 or 2 waters in. I think 1 would probably suffice. Down in the bottom, the only place that perhaps might have caught some people out was the fact that you had 2 chlorides, so you had to multiply the enthalpy of hydration of chloride ions by 2. Okay, over here, so some of you may have been a factor of 364 out. Okay, so if you got it wrong by 364, you know where you went wrong. Okay, there's a little multiple choice. Again, I'm going to move to the next screen in 3, 2, 1. Okay, so actually this was very similar to the last question, except you're asked to calculate out this time the enthalpy of hydration of the chloride ions. What you had to remember was that the enthalpy of solution was equal to the lattice enthalpy plus the hydration enthalpy of the positive ion, and then it was 2 times the chloride ion, because you had 2. So the energy deficit here was 2 times the enthalpy of hydration of chloride. So when you solved your mathematical, this part of the equation here, you had that was equal to 2x. Okay, so they've set the trap here for people who forget to divide by 2, and they've set the trap for people who get a little bit wrong in their algebra and end up out with a positive value instead of a negative value. Your enthalpies of hydration, by the way, will always be negative, so if you did get a positive value, you can go back and double check you've done something wrong. Okay, again another one, and I will pause the video in 3, 2, 1. Okay, so the first enthalpy change was, of course, the lattice enthalpy. The second one was the hydration enthalpy, but I think you need to make reference to the fact that it's hydration enthalpy of both the positive and the negative ions, the sodium and the chloride both. It's not just a hydration enthalpy, so they put them both into one equation there. And then you had to do your little Hess's law cycle. You could do it as you did it earlier, or as I did it earlier in the PowerPoint. I've just done it maybe slightly differently here, but I mean it all means exactly the same thing. That's my enthalpy of solution there. That's my lattice enthalpy there. And then these are my hydration enthalpies here and here. Okay, so this time we were trying to find out the enthalpy of solution, I think, which ends up as 5, and then I just put my final answer with the units and the sign on as plus 5. Okay, again, you might want to pause the video in 3, 2, 1. Okay, so the first one was just for the enthalpy of solution. So you're going from the 1 mole of the solid compound to the dissolved aqueous ions. And then down below, a pretty straightforward calculation. Okay, where you were calculating out the enthalpy of solution. They gave you the hydration enthalpies and they gave you the lattice enthalpy, and there was only one of each of the ions, so you weren't multiplying anything up or dividing or anything here. It was pretty straightforward. Okay, again, you might want to pause the video in 3, 2, 1. So this was we're going back to the last topic here where we were calculating out a lattice enthalpy. It was pretty straightforward. You just had to remember that the enthalpy of formation was equal to the sum of all the other enthalpy changes minus the lattice enthalpy. The only thing that might have caught you out here was they gave you here the electron affinity of 1 chloride, whereas you had to multiply that by 2 because you had 2 chlorides there. Okay, so that was the only place that might have caught anybody out. Is a Born-Haber cycle, of course. Okay, and then you had to calculate to an appropriate number of significant figures. Okay, appropriate number of significant figures. I might get marked wrong, or actually I've recorded this to 2 significant figures, but the smallest number of significant figures in the question was 3, so actually I think if my answer works out at exactly 21 there, I should have written 21.0. So yeah, just be cautious of that, guys. I wasn't paying attention to that. I could have dropped a mark possibly. So we calculate to appropriate number of significant figures the enthalpy of solution. So again, the only thing that might have caught a few people out there was the fact that because it was barium chloride is of course BaCl2. And that meant that you needed the hydration enthalpy of 2 chloride ions down there. Okay, and then it says use this to explain if barium chloride is soluble in water. Well, it's exothermic, so I think they want the connection that it's exothermic, which means that it is soluble. Okay, again, if you want to pause the video in 3, 2, 1. Alright, so calcium fluoride, the only thing that might have caught people out was the fact that the missing value was 2x's, 2 hydration enthalpies, because calcium fluoride is, of course, CaF2. So they had led the trap there. This is probably the most likely wrong answer, where people forgot to divide by 2. Some people may have multiplied accidentally by 2. That would have got them that answer. This would have been a bizarre wrong answer. It's a quarter of the actual answer. But that's the correct answer there. Okay, again, if you want to pause the video, 3, 2, 1. Okay, so your lattice enthalpy is just taken from the CA definition. You should know that well by now. And then the calculation where you're asked to calculate the enthalpy of hydration for 1 mole of chloride ions was you were after magnesium chloride. So actually it's pretty much the same question again, okay, because again you had to remember that magnesium chloride, MgCl2, so your missing energy here was equivalent to twice the enthalpy of hydration of chloride ions. You had to remember to divide by 2. And that's it. Okay guys, hope that helps and that you are able to now do not only your Born-Haber and your lattice enthalpy calculations and do all the explaining as to why something might have a high or low lattice enthalpy and why the lattice enthalpy value may differentiate from the theoretical lattice enthalpy value, but you're also able now to do your enthalpy of solution hydration calculations and explain why some substances may be soluble, some may not be soluble, and why things have high or low enthalpies of hydration. Okay, hope that helps.